Okay. So this is the second hour of Physics 1C for May 18th. And we're now going to look at an LC circuit. Okay, so an LC circuit is, as you can see, a circuit where you have only an inductor and a capacitor. Right? Only an inductor and a capacitor, and that's it. So there's no EMF source, and also there's no resistor. The fact that there's no resistor means that if at a moment in time I have some current flowing in the circuit, or if I have some charge on the capacitor, then whatever energy I have associated with those basically is going to stay inside of my circuit. That means that once we get a current flowing inside of here, the energy of that is probably going to stick around permanently. Okay. So that makes this very different from the two other circuits we've talked about up till now. We talked about RC circuits and RL circuits. The fact that there was a resistor inside of the circuit meant that stuff like this happened. Right? The current eventually disappeared. All the energy was transformed into thermal energy. That will not happen in this case. Okay. So we're going to apply Kirchhoff's loop rule to this circuit. This is the direction of travel right here. So let's start, let's say, from here. When we go to from the positive to the negative side of this, we're going to get an expression, we're going to get a term that's going to be, I think, negative Q over C. That's for the capacitor. And then we come back around past this one, we're going to get negative L di dt. And I'm going to use the current in the circuit is going to be I, that's the instantaneous current. And the charge Q is going to be the charge at a moment in time on our capacitor plate right here. Okay. That should all add to 0 according to Kirchhoff's loop rule. We are kind of cheating a little bit here, and that's something that I'm going to talk about later on. But yeah, using these inductors in this way, writing them into our loop rule equations, is a little bit deceiving. But we'll talk about that later. All right, so that's our equation. Any questions about this? So we're basically going to do just what we did before. Does this negative sign make sense on the Q over C?
Is it because you're going from the positive plate to the negative one?
I don't know. Does that seem reasonable? Let's think about it. So which plate would be higher voltage? The positive or the negative?
I would say the positive.
Positive.
Positive, okay. That's correct. So let's say the positive plate is 10 volts, and let's say the negative plate is 0 volts, okay? Then as I go from here to here, does the potential go down or up?
Down.
Down. Basically 0 minus 10 would be negative 10. So yes, the original answer was because we're going from positive to negative, that's the reason why it's negative, and that's right. Because we're going from high to low, positive to negative. Okay, so this makes sense, then that's good. So the next thing we want to do is we want to solve this equation. Now, the previous equation we solved, if we were to go back and look at it just really quickly right here, the one we started with here, this equation, we had the luxury that current, which was the thing we were trying to solve for, I, showed up in all the terms. This was current to the 0 power, and here's the current, and here's the derivative of the current. That is not happening here, because now we have a Q, and now we have an I, and our goal in this case is to find both what is the charge as a function of time on the capacitor, and what is the current as a function of time that's flowing in the circuit. Okay? So, what do we need to do to start to head down this path of solving for one of these two? And yeah, go ahead.
I was going to say, so it's like a separable, or it might be a separable differential equation, so we can separate the di and the dt.
We can, yeah, but we'd still have Q sitting around, and Q is also a function of time. So what do we need to do to this equation so we can maybe try to solve for one or the other one? Can Can we eliminate q or I in favor of the other variable? I guess is what I'm trying to say. Are q and I related to each other?
Oh, yes.
Well, yeah, di, right? Di dt, or just I is q per unit time, right?
Yeah. Current is dq dt. Okay. So we can replace I inside of here with negative q over c. We'll go ahead and move it to the right-hand side. L times ddt of I, which is dq dt. And then what we'll get is negative q over c. Let's put the L and the c on the same side, is equal to the second derivative, like that. Now, we have an equation that relates the charge q, which is a function of time, to the second derivative of the charge as a function of time, right? So we have a differential equation. This is no longer separable, though, because we have the second derivative show up right here. It's no longer separable. So we can't use the same method we used before. With this one, I don't know, you all that are taking 270, how would you approach this differential equation?
We could do like a variable substitution.
Oh?
So like d equal to like...
We're substituting for time? Is that what you said?
No.
Oh. Is there a method that you all learned in 270 to solve this type of equation?
We use a second order differential equation.
What is that?
It's the I'm trying to think of the proper term. It's the method of separation we use for an equation that has some kind of value or some kind of differentiable to the second order, which we have in the d squared.
Yeah.
Can we guess the solution?
That's what I would say. I'm asking because I want to know if you know a method. Then I want to use your method, because my method would be to guess solution. But I think what you're saying, Dawes, is that something like this, we write it like this, maybe, like, or maybe to use two dots above it. Do you guys know what this means?
Yeah, the second derivative.
Second derivative.
Second derivative, yeah. With respect to time, we use dots for time and we use primes for space. So that's basically our equation. And you were talking about a second order differential equation. Is there a way to solve this kind of like the same way you solve it's been a long time for me, so I'm trying to like hint at what you might do. Is there a way to solve this like the same way you solve a quadratic? Am I crazy? Am I misremembering something?
I know what you're talking about.
You do? So I'm not completely crazy?
No.
I'm pretty crazy, just not completely crazy. So, what were you thinking, Dawes?
It's really fuzzy for me.
Yeah.
I'm not really
Me too.
I gotta think about how to apply it. I just remember that we use this type of equation to
we can we could use a differential operator to solve it.
A differential operator, how does that work? Actually, just realized we can make these both plus, can't we? Is that where you multiple? Okay, what's a differential operator? How does that work?
Oh, okay. So you basically let the derivative act like a variable.
Right.
So it would be like d squared q plus q over LC. So then you factor out the q.
So I write this as, oh, you want me to do something like this?
No, just write a d. Just write a d.
Okay.
Because it'll get messy with just a...
So write dq with a 2 on it?
No q. Oh, yeah, that's right.
Plus q over LC, like this?
Yeah, equals 0, and then you could factor out the q.
I mean, I feel like I still need this on here, don't I? Is it okay if I go ahead and write? Because the other one doesn't have time on it, right?
It's gonna get...
Okay, if you want me to write it this other way...
I mean, it'll get messy, but
well,
it's just simpler to write a d.
I don't mind. We can fix it if we need to. So you're basically saying it's going to become this plus LC, or whoops, plus 1 over LC.
Yeah.
Times q, okay.
Okay. And now, so this is actually a difference of squares secretly, but with an I.
Yeah, so you're saying this term on the left I can write as a difference of squares?
Yeah.
Okay, so let's, if we're going to do stuff like that, I think I agree with you. We'll just leave this as d squared, but we're going to remember that this d squared represents taking the second derivative, basically, right?
Mm-hmm.
Okay, so you want me to write it as d minus I over LC times d plus I over LC?
Yeah.
Now this I is no longer the current, it is imaginary I times q equals 0. Okay.
And then this is actual. Then there's some theory, but we can actually read off the exact answer from this.
Yeah, I thought so. Okay.
Which it would be, since it's just an purely imaginary, it'd be, I'm writing it down right now.
Do we set these things equal to 0? Do we set each of these equal to 0?
You can. You can do that. I mean, it may just be quicker to...
Like, do you multiply the q back in now? Is that what you do? And then set them equal to
No.
0 and solve? No? Okay.
What is, we essentially... Well, okay. I guess you can... When you solve it to 0, you can...
I just realized
put
something.
those-
This should be square root LC, shouldn't it?
Yeah.
Sorry about that. These multiply together to give you this. Because negative I times positive I is positive 1.
And then what we basically do is we stick those zeros into the exponential function. So it would be like e to the your 0 here times t.
E to this one?
Yeah, to the or the 0 of it. Just the 0. So it would just be I over.
Just this term?
Yeah, just the 0.
The solution for
makes it
what
0?
d equals, you mean?
Exactly.
So basically you're saying d is equal to plus or minus I over square root LC.
Mm-hmm.
Whoops. And so I put the solution of what d is equal to up here.
Yeah.
Okay, so like that. And then this equals q or something?
Yeah. And we just have to stick a general constant in
Up here?
we have to as a factor.
Oh, on the front. Some constant.
And
That's
then
actually, I think this actually is the answer. Let's see if we get the same answer doing the other method. But this looks like it worked. But shouldn't there have been two solutions?
there are
Right? Plus
there
and
are
minus?
two solutions.
So
but
then
the
they
general
actually,
constant. Yeah.
it would actually become this. Q of t would become a e to the I over root LC t plus b e to the negative I over root LC t. That's what you're saying, right?
That's true.
Two different
But
constants.
these general constants just absorb the.
No, this is the
when
answer.
we do the Euler.
This is the answer. This is the right answer, actually.
I mean, when you. Well, yeah. I mean, but. Yeah, we could keep it separate.
Okay, so there is a method. That's good to know there's a method that we can go through and just do this. So basically the method was to change q double dot into kind of like the second derivative of q, like this, but then to basically factor out the q on the right-hand side, so the function is here. And now this is like an operator, but then what he was saying is, well, we can write this operator as, I mean, this is just a mathematical step, that you can write this as a difference of squares using imaginary numbers. And then now basically what we do is you basically take this and you solve for the derivative term, or what d is equal to, and then you use that as a coefficient in an e to the I expression, or e to the whatever times t expression, and that gives you your two solutions. That's pretty powerful, and the answer is correct. So let's see if we can get the same answer with your other method, which was the guess and check method, right?
Mm-hmm.
You can check to see if this satisfies this differential equation. All you have to do is to take the second derivative of this and prove that it's equal to the first derivative, or no, sorry, the function, times the negative sign divided by LC. And it should be pretty easy to see why that's the case. Maybe we should just do it. Should we just do it? So what's q dot? Q dot is the first derivative with respect to time. So if we take q dot of this entire expression, what we're going to get is the derivative of the first term is going to be 1 over root LC. You're going to get one of these. The derivative of the second term, you're also going to get that, but the difference is going to be, it's now going to be a e to the, oh, there's an I here too, sorry. Both of these are going to get an I. E to the I t over root LC plus b e to the negative I already made a mistake, I'll fix it though. LC times t. That just looks really bad. Oops. LC. This should be negative, because when we take the derivative, you're going to get a negative in front of there. This one's positive and this one's negative, so you get a negative sign. And then we take the second derivative, dq dt2, which we write as q double dot. Then we're going to get another I over LC. But this same term is going to show up again, because you have I over root LC, I over root LC. So when you take the derivative, you're going to get that term out in the front again. So you multiply I over root LC times I over root LC, you get I squared, which is going to be negative 1 over LC, because the LCs are going to, and then you basically get back the original equation. So I'm just going to boop, do like that. I didn't need to include that negative sign. But yeah, you're going to reproduce your original equation, which proves that the method that Cam kind of just talked us through works. Because if you look at that expression, it's the same thing as equals. This is the same thing as Q over LC with a negative sign, right? Because you basically just compare that one to this one. So there's the function, right? It's the same function, q double dot, multiplied by negative 1 over LC. So can you see how that satisfies this equation? Does that make sense?
The whole process is just substituting that d in, and then you factor everything out, and then you just find the roots of it, and you stick the roots in the exponential.
The exponential, yeah. Okay, this is what I remember doing too. When I was saying, can't you solve this like a quadratic, this is exactly what I was remembering doing. I just didn't know the steps. But this is the key step right here, right? To do this process, then you need to know that the solution is a constant times e to the whatever this is, whatever d ends up being equal to, right? Yeah, that's a cool method. Let's try another method and see if we can't get the same answer. So let's go down a little bit, and let's just let's start a new calculation. So this was our original work that we did. Let's copy this down here too. And let's go through the more normal way of doing this. I like that method though. That might be something that I start using in the future, because if I can kind of brush up on like the details of what this step is, then I could easily do this next time I do this. Okay, so that's one solution basically. That right there is one solution. There are more than one solution to this problem though. That's the most general solution. All right. So what's the other method? The other method is guess and check. This method will always work, 100% of the time. If you're solving a differential equation, the guess and check method is your last resort, basically. And often it is really, really challenging to do. But this equation, it's actually not that hard to do. So our goal here is to find q of t, right? So what could q of t possibly be equal to if, when I take this function, and I take the derivative twice, I get the same function back with a minus sign and an LC in the denominator. Now, in order to make this a little simpler to understand, what I'm going to do is we're going to make a definition over here to the left. We're going to let 1 over LC be equal to omega squared. This is just to make the calculation simpler. If we do that, our equation becomes negative omega squared q is equal to d2q dt2. So now, again, we're looking for a function q, that when you take the derivative twice, you get a negative sign, you get something squared, and you get back your original function. So the biggest part of this is you can kind of block out this piece and just say, what is something that when I take the derivative twice, I get the function back? What kind of function works like that? Can you think of any functions that when you take the derivative twice, you get the same function back?
A sinusoidal function.
The sines and cosines.
Sine function. Yeah, so let's try that. So our first thing that we're going to try is we're going to try a sine function. So we write in here sine of. Now, what's the sine function going to have as its argument? Well, we know it's going to have a t in here, right? And in principle, we could probably put something in front of the t, something that multiplies times the t, right? And I'm just going to try, we're just going to guess maybe that thing is going to be this thing called omega. And those of you that are really kind of keen on calculus or good at this stuff, you probably can see why we would do that. In addition, we can also, just like we did in the previous problem, we can have an overall constant we can multiply out here, because that's not going to change the derivative in any way. If I take the derivative of something multiplied by a constant, it's the function times the constant, right? The constant doesn't actually do anything. So this feels like a function that might work. And we can check, this is the guess portion, so this is our guess. Because you all thought, oh, when I take the derivative of sine, I get cosine, and the derivative of cosine is negative sine. That works out really well, because we're back to the sine function. So let's just check to see if that actually works. Are you okay if I just start using this q dot to represent derivative with respect to time?
Yeah.
Yeah, that's all good.
Okay. So the derivative of this with respect to time is going to be a times omega times the sine, nope, not sine, cosine of omega t. And if I take, that's it, right? Yeah. And then if I take the second derivative, which means we just take the derivative of this one, we're going to get negative a. When we take the derivative of the cosine, we're going to get negative sine, but we're also going to pull out an omega, so we're going to get an omega squared. And then we're back to sine of omega t. And yeah, it works, right? Because q double dot is this, and we compare that back to our original function, we can see there's our function, a sine omega t. So it is in fact the case that q double dot of t is equal to negative omega squared times q of t, right? So we've satisfied our differential equation. So this must in fact be at least one of the solutions to the differential equation right here. Of course, there are more, right? What would have stopped us from putting a cosine function here, right? We could totally have a cosine function. It would do exactly the same thing, right? Because then cosine would become sine, no, cosine would become negative sine, which will become cosine again, right? Negative cosine. So when you have, this is a differential equations question that I think you all should know the answer to. If I know that there are multiple solutions to my differential equation, so let's say I have solution 1 and solution 2. In this case, that's one solution, and then another solution would be q of t is equal to, let's use a different variable. We'll use b as our constant, times cosine of omega t. That would have worked. Are there any other functions could I have altered my function here in any way? Could I change anything about this function?
Like a phase, oh my god, like a phase angle?
Yeah, definitely. So we can put a phase angle in here. Let's see if I can select here. Let's move this to the right. Yep, so we could definitely put a phase angle in here. Let's make this a little bit longer, and then let's move our parenthesis over to the right a little bit. So yeah, we definitely could have included within here another constant that we can call phi. That's going to be our phase constant, so that's a possibility. And that's really just going to represent at what point in the motion did this all start. And we could do the same thing down here. We can drop in a phase angle. Go back to red. Maybe we use 2 different phase angles or something like that. I think we would need to, right? We need to make these different, right? So maybe call it phi 1 and phi 2. Okay, so now I have 2 different solutions that I know work. Can everyone see why the phase constant doesn't do anything? If you take the derivative, if this is a constant, it doesn't do anything, right?
True.
So if I have 2 solutions that I know are correct, how do I find a more general solution?
We take a linear combination of them.
Which is also known as just adding them, right?
Just summing them, yeah.
Summing them, right, exactly. So our actual solution then would be q of t is equal to a sine of omega t plus phi 1 plus b cos of omega t plus phi 2. And there we go. That's our answer. We're not going to use this for problems. This is the kind of like try hard answer. You know, we don't need all of this. We just know this is our most general solution. And what does it describe? Well, let's go back to the physics. It describes this circuit. It tells you that the charge as a function of time in our circuit basically obeys either this equation in red, this equation that's circled in purple, or this general equation here. Now, the equation that we're going to mostly use is just going to be Q of t. We'll just pick one of them, okay? Because one is usually more than enough to describe a system like this. So let's just choose... I like the cosine function because it starts at 1, but it doesn't really matter. So let's just choose this one. Let's choose this as our general solution. So that's what the charge as a function of time is. Then our other goal was to find the current as a function of time. And the current as a function of time is just going to be the derivative of this, right? It's q dot. So the derivative of this is negative a omega sine of omega t plus phi. So there's that, we've now solved it. This tells us how the current obeys as a function of time and how the charge obeys as a function of time. They look like cosine functions. So remember that Q represents, let's say that Q represents just the charge on this left plate right here, right? If we now plot what that looks like, well, I mean, obviously it looks like a cosine function, but let's plot it and talk about it. So here's our graph. So if we want to plot, let's say charge as a function of time on the left capacitor plate over here, then what this tells us is that at t equal to 0, let's let phi equal to 0 to just keep things simple. So we'll just go with, for now, we're going to use phi equal to 0. If phi is equal to 0, then we just have a cosine omega t, and what that's going to look like is just your normal cosine function, which is going to go from here down to here and back up to here again, like this, and then it's going to repeat, right? It'll do the same thing. And back up to here again. And we'll know that each of these time intervals right here, where the time is going to represent, for example, this is going to be t equal to 1 period. And this is going to be t equal to half of the period. And what is the period? Well, the period is equal to 2 pi divided by this angular frequency right here, omega. Which we know what it is, right? Because this was our definition. The angular frequency is related to L and C, the inductance and the capacitance. We'll come back and talk about this in just a second. But this is what it looks like. So what's going to happen on my circuit is that it's going to start off with a positive charge on the left plate, and then that charge is going to drop to 0, so the capacitor is completely uncharged. Then the polarity of the capacitor is going to reverse, right? So here, I could maybe, I don't know if this is helpful, but what I could do is I could be like, this is what my capacitor looks like. Here I've got plus Q and minus Q on the capacitor, right? When I get to here, you've got Q equal to 0. When I get to here, it's negative Q plus Q. And then when I get to here, we're at 0 again. And when I get back to here again, we're back to the original configuration, plus Q and minus Q. I don't know if that helps. But that's what's going on. The charge on the plate is positive, and then it's 0, and then it's negative, and then it's 0, and then it's positive. And the current's doing something similar. The current starts off at 0, and then it becomes negative I max, and then it becomes, so yeah. And another thing that we can say about this circuit is that this quantity right here, A, right, it actually means something. In our case, A is basically going to represent, what does it represent now? It's physically means something. What does our amplitude A represent now?
I max.
No.
Or,
Close.
Negative. Oh, that A. Oh, not A omega. It's just the max charge.
This is max charge, and then A times omega has to be max current, right?
Yeah.
So we now have a couple equations that we can, say something about. I max is now equal to omega times A, but A is Q max, right? So it's omega times Q max. That's how you find the current. If you know the frequency, then you can find the current if you know the charge. That's basically what that equation says. And that allows us to kind of rewrite what these equations say. So now, in general, what our equation says, since we know that the amplitude is actually related to something physical, we can now say basically Q of t is equal to Q max times cos omega t plus phi. And I of t is I max times, well, negative I max sine omega t plus phi. And those are our equations. Now, we can observe this, because we can construct a circuit like this in PhET, and we can actually see what this looks like. Assuming I can get this to work without it breaking on me. I think this is what we want. We want this one. I don't really know what the difference between the one that's a virtual lab and the one that's not is. They look pretty similar. So all we have to do is just get a circuit with an inductor and a capacitor, and what this tells us is that the charge on the capacitor is basically going to kind of bounce back and forth through the circuit. That's what's going to happen. So we need a capacitor, and we need an inductor, and then we need to connect them. And we need to charge up the capacitor. All right, I don't want this current flowing through the top circuit to begin with, so what we'll do is we need a battery to charge up our capacitor. And what I'm going to try to do is to just charge it and then remove the battery. There it goes. It's charged. Okay, now it's charged, but the current's not, or the charge isn't going anywhere because there's no path for it to escape the system. So now we start off with our left plate fully charged, and maybe I should. Do you guys care if the inductor's on top or bottom? Does that matter at all? Sounds like it doesn't matter. No one's really throwing a fist or anything. Okay, so
No, not really.
So capacitor's fully charged, right? So now what we're gonna do is we're gonna watch what happens. And in fact, let's put our current chart on here so we can actually look at what's happening with the current in our circuit here. Obviously, there's no current now, but we're gonna create a path for current by closing this because now our capacitor is gonna act as an EMF source. And let's see what happens. All right, 3, 2, 1. We're gonna zoom in here so we can see this better. The features of this. Look how beautifully perfect of a sine function this is.
Is this an alternating current?
Yes. This is alternating current, 100%. This is like pure alternating current. Because the current it's alternating, right? The current is 0, negative, whatever. What's our maximum? Looks like about 0.5. So it goes from negative 0.5 to 0 to positive 0.5, and then back to 0, and it just alternates back and forth and back and forth and back and forth. It's kind of beautiful, you know. If you watch what's happening here, it's like it gets charged up, but then eventually there's so much charge that you can't pile any more on, and so the current basically flows the other way until it's reverse charge, and then it kind of like. Remember that the balls here are electrons, so the path of the balls is going to make things more negative, right? So when the balls flow into something, it's going to become negative, but they flow as far as they can, and then they get pushed back because they're negative, and they're trying to push themselves into it, so then they flow back into this one. Current drops to 0, but then the current picks up again. When this is 0 charge, the current's at maximum, and it flows back here. So yeah, alternating current. One thing I like to think about this as is like, as these charges flow into this thing right here, you notice that like the rate at which they flow in slows down. Can you all see that? Just watch the charges as they flow into here. They're flowing in really fast, and then they're kind of like slowly building up until there's so many negative charges that it pushes back. So I like to think of the capacitor in this system. First of all, let's just acknowledge that this capacitor is doing much more than capacitors have done for us in the past, right? I mean, normally capacitors just basically charge up and then they're done, right? They don't do anything. They charge up and they're done, right? But this capacitor is continually doing something in the circuit. And this is one of the things about alternating current that Cam mentioned that's so interesting, is that when a capacitor is subjected to this type of a current, it no longer prevents the flow of current instead what it does is it kind of redirects it, you know? It makes the current which was flowing this way have to be eventually pushed back and flow the other direction, right? And in this sense, I think that this circuit acts a lot like a mass and a spring that we talked about with a simple harmonic oscillator. If you think about the motion of these balls right here, and you think about the capacitor as being like a spring, right? The balls, basically the electrons, try to flow into that capacitor, which creates a compression of energy, just like a spring, and then eventually they flow back the other way, right? It's like you're pushing these things as hard as you can, you're tightening up that spring, and then the spring expands and pushes back out until it pushes back the other direction, basically. So this is your LC circuit, and it's really kind of fascinating. Now, this circuit, what's the reason why the max current and the min current aren't decaying? Like, why is it that this thing hasn't run out of energy yet? I mean, it looks like a perpetual motion machine almost, really, right? It's not slowing down. The energy is just basically going back and forth and back and forth.
Zero resistance.
Zero resistance, exactly. The inductor and the wires, in this case, are acting as superconductors. They have no internal resistance, which means the energy of this system is going to stay constant. Now, we've learned how you can store energy in an inductor and how you can store energy in a capacitor, right? And we can talk about the energy storage that's happening here, right? Because the way this works is that the energy stored in the capacitor is given by basically the charge on the capacitor squared over 2C, and the energy stored in the inductor is given by, I think we derived this last time, 1/2 L times the current squared, right? So what's happening is that when the charge drops to 0, like here and here, there's no energy in the capacitor. So where is it? Well, it must be in the inductor, right? And when the current reaches 0, which happens when the charge reaches maximum, now all of the energy is in the capacitor. So what you have happening is, coming back to here, all the energy in the capacitor, now all the energy in the inductor for just a moment, back to all energy in capacitor, wait till this drops to 0, now all of the energy's here, and then now all the energy's back here. So you're taking energy in an electric field and then converting it over to energy in a magnetic field, back to electric field to magnetic to electric to magnetic, basically, right? You're exchanging energies between these two objects. And we have a little schematic. Normally I would just draw this, but since your book has this nice schematic, we're going to use this. It'd be very time consuming to draw this all out anyway. Might be more useful. You know, I kind of feel like I should just draw it out. We need to take a break though, don't we? Yeah, let's just take a break. Let's take a break. It's 4:05. We'll take a break to 4:15, and when I come back, we'll map out how the energy is happening here, and then we're going to directly compare what's happening to the simple harmonic oscillator. Okay, any questions before we take a break?
Is it fine to, like, oh,
Go ahead.
Oh, sorry.
Go ahead, Kenny.
I was just wondering, like, when you drew the curve, like, could you explain, like, why'd you labeled it like positive Q and then negative Q and then like?
Sure. So our equation says Q as a function of time is equal to Q max times cos omega t plus phi, right? And what I was saying is, well, what do we mean by Q in this case? Because there's technically two things that have charge. There's the left side and the right side of the capacitor plate. So I said, let's let this define the left side of the capacitor plate. So a sine function, or in this case a cosine function, has the effect of going from, oh, you know what, something I didn't write on here that might actually clarify what's going on here. This is positive Q max, so the maximum charge on the capacitor, and this is negative Q max. So what this curve tells us, what the function tells us, is that the charge on the capacitor starts off as positive, and then it becomes negative, positive, 0, negative, 0, positive. So you go through a cycle where it's the charge on the left plate is positive, and then it drops to 0, and then it becomes negative, like that. Does that answer your question?
Okay, yeah. It's just it makes sense why you labeled it that way. Okay.
Yeah, and these little things are supposed to be the capacitor, basically.
Yeah, the plates.
The plates. Right. Yeah, the plates. And did you have a question, Kim?
I was just gonna ask, is it like fine to leave like the answer as like e to the I something? in physics? Or
Oh yeah, sure. I mean,
What's
this
the
this
consensus?
other equation is totally acceptable. We didn't get back to that. But we can come back and talk about that after the break. But yeah, I mean, this equation right here also works. 1 over square root LC is omega, right? So this is basically a e to the negative positive I omega t plus b e to the negative I omega t. And I left out a phase because we could have had a phase here, right? But in physics, yeah, sometimes people describe these with this, or they might say it's the real part of this or something like that, right? Because as you know, this equation can be written like this, right? Just you'd have plus a times negative I and b times negative I, right? Times this cosine and sine. Because e to the, what is it? E to the it is basically cosine t plus I sine t, right? So your question is, do people in physics just use this instead of using this? And yeah, they do. Sometimes, not always. They're both perfectly acceptable solutions, right?
Yes, yes.
They both say the same thing, basically, because we can rewrite this as an exponential function, right? Because the sine of omega t plus phi 1 is e to the I times this, what is it, minus e to the negative I times this divided by 2i or something like that, right?
Yeah, that's right.
So, and then we can write this as an exponential function as well, and then get back to here. I can say in general, in terms of what physicists do, from my experience of working with some of these type of things, and not necessarily in electromagnetics, but also in quantum mechanics, stuff like that, because similar solutions show up, is that physicists use whichever one is going to help them to solve the problem. So sometimes what you have to do is what I just described. Really common thing you have to do, and really when these problems get trickier, which happens when you take your upper division like electromagnetism courses. These you end up with a lot of problems where they say like, prove that the current in this circuit is going to look like blah 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 or whatever, and prove that this is true. And usually what you end up having to do is to basically kind of decompose all of your sines and cosines into exponential functions, do a bunch of calculus and math, and then rewrite them as sines and cosines at the end, or leave them as... Does that make any sense?
That makes sense, yeah.
Yeah, so like we treat these as equivalent expressions, which means that if you need to, you can break this up into exponential functions, and there's a lot of reasons to do that. It can help you from having to use the horrible thing of trig identities, right? Because as soon as you start writing things as exponentials, what were before trig identities are now just algebra, right? So that's my memory, is when I got to the really hard stuff in electromagnetism, the trick that I learned was just to write everything in exponentials, do all the math, and then at the very end you can convert them back to sines and cosines if you need to. But usually you didn't. And that was always really fun.
That is a good idea.
Because I'm kind of sadistic or masochist or whatever the right word is in terms of my love of doing algebra. It's very fun for me. Anyway, so let's go